A modern large language model, packing 70 billion parameters, is essentially a massive, frozen snapshot of the internet. We call this parametric knowledge. Every piece of information the model learned during pre-training is mathematically baked directly into its static weights and biases. But this architecture creates immediate bottlenecks. If you ask the model about your proprietary codebase or internal corporate documents, it will fail. It cannot retrieve what was never in its pre-training data. It also suffers from a strict knowledge cutoff. Because the weights are frozen the moment training ends, the model is intrinsically locked out of learning any post-training events. So while this massive parametric memory contains a vast understanding of human language, its static nature makes it completely unsuited for dynamic, real-world enterprise applications that rely on constantly updating information. When you force a model to rely entirely on this static memory for topics it barely knows, it resorts to guessing. This creates a probabilistic misfire, known as hallucination. Take Albert Einstein. If you ask a standard model about his early life, you expect a factual history. Instead, the model might confidently tell you that Einstein played professional football for Germany. The predictive text engine prioritizes generating a sequence of words that sounds plausible, completely bypassing factual accuracy. This leaves us with a difficult engineering problem. How do we inject precise, private data and stop these hallucinations without spending millions to rebuild the entire model from scratch? The answer requires us to stop relying on the model's static memory and instead focus entirely on the data we feed it at the exact moment we ask the question. Historically, the solution was supervised fine-tuning. You would curate a new dataset and retrain the model to update its weights, a highly inefficient and expensive loop. But researchers noticed an alternative behavior in models that reached a certain scale. This timeline graph maps parameter scale against capabilities. As models cross the 175 billion parameter threshold, like GPT-3, an emergent capability activates. The model gains the ability to learn entirely new tasks simply by reading examples provided inside the prompt itself. Developers realized they could exploit this property. Rather than retraining the model to learn facts, they could inject dense, domain-specific information directly into the prompt payload. By pushing the right facts into the prompt window, we bypass the need to alter the model's underlying weights. This diagram illustrates the 4 phases of Retrieval Augmented Generation, or RAG. We'll use a 2-hour video transcript on linear regression as our data source. Phase 1 is indexing. We ingest the transcript and apply text chunking, slicing the document into smaller, bounded paragraphs. We have to chunk the data because language models have strict limits on how much text they can read at once. Furthermore, performing semantic search on one massive document yields incredibly poor accuracy. Next, these text chunks pass through an embedding model, translating their semantic meaning into dense vector arrays. Finally, we store these arrays in a specialized vector database. By plotting them into a mathematical coordinate space, we map relationships between concepts. This completes the asynchronous indexing phase. We have successfully taken human text and built a mathematically searchable external knowledge base. With our index built, we shift to the real-time inference phase. It begins the moment a user submits a specific query. The user asks, how do we perform the optimization step in gradient descent? To search our database, we convert this question into its own vector array using the identical embedding model. This triggers phase 2, retrieval. The query vector drops into the 3D coordinate space of our vector database. By calculating cosine similarity, the system measures the physical distance between the query and the stored data, extracting only the specific chunks that discuss gradient descent. The system has successfully isolated the exact contextual needle from the data haystack, relying purely on mathematics rather than the model's static memory. Now we reach phase 3, augmentation. We cannot send raw text chunks blindly to the model. They have to be structured. Looking at this generated prompt payload, we see the strict system instructions placed at the top, the retrieved gradient descent text sitting in the middle as context, and the user's query at the bottom. The instructions include a critical constraint. We tell the model, answer only from the provided context. If it is insufficient, state you do not know. This brings us to phase 4, generation. The fully augmented prompt is fired off to the pre-trained language model. The model reads the input. It uses its parametric knowledge simply to reason and generate natural language, but it relies entirely on the injected context for its factual basis. By doing this, RAG restricts the model to the provided dataset. It utilizes the LLM as a tool for interpreting retrieved facts, rather than a primary source for the facts themselves. When managing dynamic data at an enterprise scale, architectural decisions carry serious financial implications. On the left, traditional fine-tuning requires a cyclical, GPU-heavy retraining loop every time data changes. Compute costs rise rapidly. On the right, RAG bypasses the network entirely. New data is simply converted into a vector and dropped into the database. The cost graph remains flat. For environments with frequently changing data, like a daily newsfeed, RAG allows for near instantaneous updates to the knowledge base without the need for expensive GPU time. Updating a vector index is cheaper, faster, and more modular than continually adjusting a massive model's weights. This brings us back to the three inherent failures of relying purely on parametric memory: inaccessible private data, rigid knowledge cutoffs, and hallucinations. RAG bypasses the private data and cutoff limitations effortlessly because it sources facts directly from an external database that you control and update continuously. Enforcing a strict augmentation payload grounds the model's response in the provided text, which limits its ability to fabricate information. Retrieval Augmented Generation bridges the gap. It combines the modularity of classical information retrieval with the linguistic processing of modern generative models.